What if the next great chapter of human civilization wasn't written on Earth, or even on a rocky planet like Mars, but inside the swirling, chaotic depths of a gas giant? Picture a world where cities float among hydrogen clouds, where storms rage with the energy of 1,000 suns, and where life doesn't just survive but thrives in conditions we once thought impossible. Gas giants like Jupiter and Saturn have long fascinated us with their colossal scale and violent beauty, but could they ever become more than cosmic wonders? Could they one day be home? These monstrous planets are nothing like our own. Imagine an atmosphere so thick and turbulent that it crushes, churns, and burns anything in its path, a place where pressures could flatten a submarine like a soda can, and temperatures swing from freezing to furnace hot in mere miles. Yet within that chaos there might be hidden layers, regions where the conditions are just right, pockets of stability, vast oceans of exotic materials, or even floating habitats riding the eternal winds. The idea of a civilization living inside a gas giant sounds like pure science fiction, but when we break it down, the science behind it is stranger and more fascinating than any fantasy. This isn't just about survival, it's about reimagining what life could be. Think of the creativity, the technology, and the sheer audacity it would take to build a society suspended in a sky without end. What kind of architecture would withstand hurricanes larger than Earth? How would we harness the raw power of a planet that radiates more heat than it receives from the sun? And most tantalizing of all, could there already be forms of life entirely alien to us, drifting unseen in those endless clouds? The questions alone ignite the imagination. So let's dive deep, not just into the science, but into the breathtaking possibilities of what might await us in the heart of a gas giant. Gas giants are unlike anything we experience on Earth. These colossal planets, like Jupiter and Saturn, are massive spheres of swirling gases with no solid ground beneath, just layer upon layer of crushing atmosphere, growing denser and hotter the deeper you go. Instead of rock and soil, their composition is a mix of hydrogen and helium, along with traces of other gases like methane and ammonia. Picture an endless ocean of these elements, but one where the pressure and temperature turn simple gases into bizarre, unfamiliar states of matter. For comparison, imagine standing on Earth where you can feel the ground beneath your feet, dig into soil, or climb a mountain. On a gas giant, there's no such thing as solid land. If you tried to land on Jupiter, you'd just keep sinking, passing through bands of colorful clouds, violent storms, and regions where hydrogen becomes so compressed it behaves like a liquid metal. The sheer size of these planets is staggering. Jupiter alone could swallow over 1,000 Earths, and its storms rage for centuries, with winds reaching speeds we can barely fathom. The Great Red Spot, a hurricane larger than our entire planet, has been churning for at least 400 years, a testament to just how different these worlds are from our own. Adding to their alien nature, gas giants generate intense magnetic fields, some thousands of times stronger than Earth's. These magnetic shields trap radiation and create dazzling auroras, but they also make spaceflight near them hazardous without heavy shielding. All of this paints a picture of a world that seems utterly hostile to life, yet within that chaos, there could be regions where conditions stabilize, where pockets of possibility exist. The deeper mysteries of gas giants challenge our understanding of what a planet can be and force us to rethink the very definition of habitable. Living inside a gas giant isn't just daunting. It's like trying to build a house in the heart of a nuclear explosion while being crushed by an ocean. The first hurdle, pressure. On Earth, we experience about 1 atmosphere of pressure at sea level, but descend into Jupiter's clouds and that number skyrockets. Just 150 kilometers down, the pressure reaches 1,000 times Earth's surface level, enough to crumple a battleship into a ball of scrap metal. Go deeper, and hydrogen gas gets squeezed into a bizarre metallic state. a form of matter so alien it conducts electricity like copper while behaving like a liquid. No known building material could withstand that relentless force without being pulverized or melted beyond recognition. Then there's the heat. Gas giants might seem cold from space, with cloud-top temperatures hovering around -150 degrees Celsius. But dive beneath those outer layers and things turn apocalyptic. Jupiter's core simmers at temperatures hotter than the surface of the Sun. Some estimates suggest over 20,000 degrees Celsius. That's not just inhospitable, it's a furnace where even tungsten, one of the most heat-resistant metals, would vaporize instantly. Unlike Earth, where temperature changes gradually with altitude, gas giants have layers of extreme cold and blistering heat stacked atop each other, creating a gauntlet of thermal extremes. Radiation adds another nightmare. Gas giants generate magnetic fields so powerful they trap charged particles, forming lethal radiation belts. Jupiter's radiation is thousands of times more intense than Earth's Van Allen belt, enough to fry unprotected electronics in hours and deliver a fatal dose to humans in minutes. Even robotic probes like Juno must hide behind thick titanium shielding to survive brief passes through these zones. For any long-term habitat, shielding would need to be absurdly heavy or rely on physics we haven't mastered yet, like deflecting radiation with force fields. And let's not forget the wind. The upper atmospheres of gas giants are shredded by hurricanes the size of continents, with winds exceeding 600 kilometers per hour. These aren't temporary storms, they're permanent features, chaotic and unpredictable. A floating city would need to anchor itself somehow, but in an environment where up and down are meaningless and the very air around you is a supersonic blender, traditional engineering fails. Even if we could design a structure to survive, keeping it stable in a maelstrom that makes Earth's worst tornadoes look like gentle breezes is a problem with no obvious solution. Yet within this catalogue of horrors, there's a glimmer of possibility. Certain regions, like the layers where temperature and pressure approach survivable ranges, might offer narrow windows for floating habitats. Some scientists speculate about using balloons filled with breathable air or advanced aerogels to create buoyant enclaves. Others suggest tapping into the planet's own energy, harnessing the heat differentials between layers to power cities. But even these ideas require technologies so far beyond our current capabilities, they might as well be magic. The challenges are less engineering puzzles and more like rewriting the laws of physics. Still, if history teaches us anything, it's that impossibility is just a temporary condition. The concept of floating cities inside gas giants might sound like pure fantasy until you realize we've been dreaming about them for decades. Take Bespin from Star Wars, a glittering metropolis hovering in the clouds of a gas giant, where ships dock on landing platforms and life goes on high above the crushing depths below. It's a stunning vision, but could it ever be more than fiction? Surprisingly, scientists have already sketched out real-world proposals for cloud-based habitats, not for gas giants, but for Venus, where the upper atmosphere is surprisingly Earth-like in temperature and pressure. If we can imagine floating cities on Venus, why not push the idea further into the violent skies of Jupiter or Saturn? The key lies in the upper layers of a gas giant's atmosphere, regions where the pressure and temperature aren't instantly lethal. Unlike the inferno deeper down, these zones might offer narrow bands of relative stability. Picture a habitat buoyed by the surrounding gases, like a hot air balloon floating in an endless sky. Instead of fighting the planet's crushing gravity, such a structure could ride the winds, using the dense atmosphere itself for lift. The idea isn't as far-fetched as it seems. On Earth, we've built airships that stay aloft for months, and advanced materials like graphene or aerogels could theoretically create lightweight yet ultra-strong enclosures capable of withstanding the chaotic weather. But gas giants don't play by Earth's rules. Even in the gentler upper layers, winds scream at hundreds of kilometers per hour and storms the size of continents churn without end. A floating city wouldn't just need to stay aloft, it would need to navigate a permanent hurricane, one speculative solution harnessing the planet's own energy. Gas giants radiate more heat than they receive from the sun, creating massive temperature differentials between atmospheric layers. A habitat could tap into that energy, using thermal updrafts to stabilize its position or even generate power. Imagine a city that doesn't just survive the storm but learns to surf it, using the planet's fury as its engine. Then there's the question of materials. On Earth, we build with steel and concrete, but in a gas giant's atmosphere, traditional construction would be useless. Instead, future engineers might rely on self-repairing nanomaterials or structures inspired by deep-sea creatures that thrive under immense pressure. Some theorists suggest using gas giant atmospheres themselves as a resource, mining hydrogen for fuel or harvesting rare molecules formed under extreme conditions. The cities of tomorrow wouldn't just float, they'd evolve, adapting to their environment in ways we can barely envision today. Of course, the biggest challenge isn't just engineering, it's psychology. Humans aren't built for life without horizons. On Earth, we're grounded by gravity, comforted by the solidity of land. In a gas giant, there's no ground, no sky, just an endless ocean of clouds stretching in all directions. A floating habitat would need to simulate the rhythms of terrestrial life, from artificial day-night cycles to communal spaces that counteract the disorientation of living in perpetual suspension. The mental toll of such an existence is hard to predict, but history shows we adapt to even the most alien environments given time and ingenuity. What's fascinating is that gas giants might not even need human inhabitants to host life. Some astrobiologists speculate that these planets could harbor floating, microbe-like organisms, creatures adapted to swim through dense atmospheres, feeding on chemical energy or lightning discharges. If such life exists, it would redefine our understanding of biology, proving that life doesn't need solid ground, sunlight, or even water as we know it. A gas giant civilization might not look like Bespin's towers and starships. It could be something far stranger, a network of organic habitats drifting and evolving in the eternal storm. The dream of floating cities forces us to confront the limits of our imagination. We're so used to thinking in terms of planets with surfaces that the idea of a sky-bound civilization feels alien, almost unsettling. But if humanity ever takes this leap, it won't be about conquering a gas giant, it'll be about learning to coexist with an environment that defies every instinct we have. The technology might be centuries away, but the vision is already here, whispering to us from the edges of science and fiction alike. Whether we'll answer that call is a story still waiting to be written. Diving into the atmosphere of a gas giant is like peeling an onion. Each layer reveals something radically different from the one before. At the top, you'd encounter the troposphere, a churning soup of clouds made of ammonia, water, and hydrogen sulfide, where storms rage with winds faster than any hurricane on Earth. This is the realm of perpetual turbulence, where temperatures plummet to bone-chilling lows and pressures start their relentless climb downward. Not exactly prime real estate for a floating city. But descend further and things get interesting. Beneath the chaos of the troposphere lies the stratosphere, where temperatures stabilize slightly and the atmosphere becomes less violently mixed. Here, the pressure is still crushing by Earth standards. Think deep ocean trenches, but with hydrogen instead of water. Yet some theorists suggest this could be the Goldilocks zone for floating habitats. The stratosphere's relative calm, compared to the maelstrom above, might allow for buoyant structures to maintain position without being shredded by winds. Picture a habitat riding dense updrafts like a cosmic hot air balloon, its outer shell reinforced to handle pressures that would crumple conventional materials. Then there's the thermosphere, where temperatures spike dramatically due to the planet's internal heat and intense radiation. Sounds hostile, right? Paradoxically, this layer's extreme heat could be an asset. The temperature gradient between the thermosphere and cooler layers below might be harnessed for energy, powering cities that float at the boundary between boiling and freezing. Imagine fusion reactors tapping into the ambient hydrogen, or thermal drones harvesting energy from the differential-like underwater vents feeding deep-sea ecosystems. But the real wild card is the hypothesized mushball layer, a region where ammonia and water vapor condense into slushy, semi-solid globs. Recent data from probes like Juno suggests this layer might exist on Jupiter, creating pockets of bizarre, slush-like stability amid the chaos. If true, it could act as a natural anchor point for habitats, a scaffold in the sky where structures could tether without being torn apart by winds. Of course, stability is relative. Even the mildest layers of a gas giant are still realms of unimaginable force. A habitat here wouldn't just need to float, it would need to adapt like a living organism, shifting with atmospheric tides and weathering storms that last centuries. The engineering would border on alchemy, materials that self-heal when damaged, AI systems predicting wind shear microseconds before it strikes, and cities designed to drift like dandelion seeds in a hurricane. And let's not forget the view. A civilization nestled in these layers wouldn't see a sunlit sky or a starry night. Instead, the horizon would fade into an endless expanse of swirling gases, lit by perpetual lightning and the eerie glow of auroras dancing along magnetic field lines. Day and night would be artificial concepts marked by the pulse of city lights rather than celestial cycles. It's a world where home isn't a patch of ground but a bubble of order suspended in an ocean of chaos, a testament to life's ability to carve out niches in the most unthinkable places. The deeper we look, the more gas giants defy our expectations. What seems like a hellscape at first glance might just contain hidden oases, layers where the fury of the planet gives way to fleeting moments of equilibrium. Finding them isn't just about brute force engineering. It's about learning to think like the atmosphere itself, to bend without breaking. And if we ever crack that code, the rewards could be staggering. Unlimited hydrogen fuel, exotic materials forged under extreme pressure, and perhaps even answers to the oldest question of all. Are we alone? Because if life can cling to a floating city in Jupiter's clouds, who's to say it didn't get there first? Surviving inside a gas giant would demand more than just sturdy structures. It would require harnessing energy on an unimaginable scale. Thankfully, these planets are practically overflowing with raw power, if only we could tap into it. The most obvious source, the atmosphere itself. Hydrogen makes up nearly 90% of a gas giant's composition, and in its compressed, metallic form deep beneath the clouds, it could fuel fusion reactors far more efficiently than anything on Earth. Imagine reactors that don't need scarce isotopes like deuterium or tritium, but instead siphon the planet's own hydrogen, turning the endless ocean of gas into a self-replenishing power grid. The catch: fusion technology is still in its infancy, and doing this under crushing pressures and supersonic winds would make even experimental reactors on Earth seem simple by comparison. Then there's the kinetic energy of the storms themselves. Gas giants are engines of perpetual motion, with wind speeds that dwarf Earth's most violent hurricanes. A single storm on Jupiter releases more energy than humanity consumes in a century. Capturing even a fraction of that could power civilizations, but the engineering hurdles are staggering. Traditional wind turbines would snap like twigs in 600 km/h gusts, and without a fixed surface to anchor to, any generator would need to ride the currents like a kite in a tornado. One radical idea involves floating wind farms with turbines made from hyper-elastic materials, their blades flexing with the winds rather than resisting them. Think of seaweed swaying in a current instead of a rigid tree in a storm. Another proposal, electrodynamic tethers, long conductive cables that generate electricity as they're dragged through the planet's intense magnetic field, essentially turning the atmosphere into a cosmic-scale dynamo. But perhaps the most intriguing possibility lies in the thermal gradients between layers. Gas giants are heat factories, radiating more energy than they absorb from the sun. The temperature difference between the freezing upper clouds and the scorching depths below could span thousands of degrees, a potential goldmine for energy harvesters. Thermal drones or floating power stations could exploit these differentials, using heat exchangers to generate electricity, much like ocean thermal energy conversion on Earth, but on a planetary scale. Picture a city powered not by solar panels or nuclear plants, but by the planet's own simmering core, its energy drawn upward through massive floating heat sinks. And let's not overlook the wild cards like lightning. Jupiter's thunderstorms unleash bolts 1,000 times more powerful than Earth's, with discharges so vast they dwarf entire cities. Capturing that energy would require networks of superconducting antennas suspended in the storm zones, a concept that borders on science fiction. But if perfected, it could provide bursts of power so intense they'd make terrestrial grids look like candle flames beside a bonfire. The irony is delicious. A gas giant's most hostile features might also be its greatest gifts. The same winds that tear apart structures could spin generators for millennia. The crushing pressures that liquefy metals might also compress hydrogen into fusion-ready fuel. Even the radiation belts deadly to unshielded life could be mined for high-energy particles. The key isn't fighting the environment, it's collaborating with it, designing systems that don't just endure the chaos but thrive on it. After all, if life here is possible, it won't be because we conquered the storm. It'll be because we learned to dance with it. Building a floating city in a gas giant isn't just about finding the right location. It's about creating materials tough enough to laugh in the face of a planet that chews up diamonds like candy. The corrosive atmospheres, hurricane-force winds, and crushing pressures demand substances far beyond steel or concrete. We'd need materials that don't just resist destruction but actively defy it, blending strength, flexibility, and self-repair in ways that sound straight out of a superhero's toolbox. Take nanomaterials, for instance. Structures built with carbon nanotubes or graphene could be hundreds of times stronger than steel while weighing almost nothing. A critical advantage when every extra gram risks dragging your habitat deeper into the abyss. These molecular-scale materials might form the skeleton of floating platforms, their lattice-like structures dispersing stress across countless microscopic bonds. Picture a skyscraper woven from diamond threads, bending like a reed in the wind instead of snapping under pressure, but even these wonder materials have limits. Gas giants don't just crush, they corrode. Ammonia clouds and hydrogen sulfide would eat through conventional metals like acid, demanding coatings or alloys engineered to shrug off chemical attacks. Imagine a building's outer skin that regenerates like living tissue, its surface molecules rearranging to patch holes before storms can exploit them. Then there's aerogel, the lightest solid known to science, with insulating properties so potent it could shield habitats from both the deep freeze of upper clouds and the inferno below. A city encased in aerogel might resemble a cosmic dandelion, its delicate-looking structures deceptively robust, but adapting it for gas giants would mean reinforcing its fragility, perhaps by infusing it with nanofibers or creating hybrid materials that borrow aerogel's lightness while adding the toughness of synthetic spider silk. The real game changer, self-repairing structures. On Earth, scientists are already experimenting with materials embedded with microcapsules of healing agents or bacteria that secrete limestone to fix cracks. In a gas giant's environment, such systems would need to work at warp speed, sealing breaches before hurricane winds rip them wide open. One speculative concept involves programmable matter, substances that shift their atomic configuration on command, allowing a damaged wall to reconstitute itself like liquid metal reforming after a bullet passes through. Durability isn't just about surviving impacts, it's about evolving with them. A gas giant's atmosphere isn't a static enemy, it's a shape-shifting opponent that changes tactics by the second. Future habitats might mimic deep-sea creatures like the Yeti crab, whose flexible exoskeletons withstand pressures that would implode most submarines. Or they could take cues from extremophiles in Earth's harshest environments, organisms that thrive in boiling acid or crushing darkness. The lesson, survival here isn't about brute strength, it's about dancing with chaos, building structures that treat the storm not as a threat but as a partner in an endless lethal waltz. The irony is profound. To conquer the most hostile places in the solar system, we might need to stop building like humans and start building like the planet itself, crafting materials that embrace fluidity, resilience, and a touch of madness. Because in a world where the sky is both ocean and earthquake, the only way to last is to learn how to bend without breaking and then bend some more. Gravity on a gas giant isn't just a force, it's a relentless, bone-crushing embrace. Jupiter's gravity, for instance, is 2.5 times stronger than Earth's, turning even simple movements into Herculean tasks. Picture trying to stand under the weight of an invisible car pressing down on your shoulders, where a morning jog could feel like sprinting through wet concrete. The human body, optimized for Earth's gentle pull, would deteriorate fast under such strain, muscles wasting, bones thinning, and organs struggling against the constant drag. Yet, if we're serious about calling a gas giant home, adaptation isn't just an option, it's survival. Traditional solutions like exercise or drugs would barely scratch the surface. Astronauts on the International Space Station lose bone density at alarming rates despite rigorous workouts, and that's in microgravity. Now flip the script, high gravity would compress spines, strain hearts, and turn even lifting a fork into a workout. Enter genetic engineering, a potential game changer. Scientists are already exploring ways to tweak human DNA for resilience, from strengthening bone density by activating genes found in animals with extreme load-bearing adaptations like elephants, to enhancing muscle fibers based on traits seen in powerlifters or sprinting cheetahs. Imagine splicing in biological shock absorbers like the collagen-rich tendons of kangaroos to help joints withstand relentless pressure. The ethical hurdles are massive, but the science isn't pure fantasy. For those wary of rewriting their DNA, mechanical augmentation could offer a stopgap. Advanced exoskeletons, far beyond today's clunky prototypes, might redistribute gravitational load across reinforced frames, turning a crushing 2.5 GS into a manageable sensation. Think of it as wearing a high-tech diving suit, one that counteracts gravity's pull with hydraulics or electromagnetic resistance, turning every step into an assisted glide. The catch: power. Gas giants lack easy access to fossil fuels or solar energy, meaning exoskeletons would need to tap into the planet's own turbulent atmosphere for juice, perhaps using kinetic energy from wind or thermal differentials. Then there's the wild card: redesigning humans from the ground up. If natural adaptation takes millennia, why not accelerate it? Synthetic biology could craft a new branch of humanity. Beings with reinforced cardiovascular systems, compact, dense musculature, and circulatory networks fine-tuned to resist gravity's tyranny. Their bodies might resemble Earth's deep-sea creatures, built to thrive under pressures that would kill unmodified humans. This isn't just about survival, it's speciation, a fork in the evolutionary tree. But let's not forget the psychological toll. High gravity doesn't just bend bodies, it warps perception. Time might feel slower under such weight, movements deliberate and labored. The constant effort could shorten tempers, strain mental health, and reshape social dynamics in ways we can't yet predict. Early settlers might rely on virtual reality or drugs to simulate the lightness of Earth, clinging to memories of open skies and effortless steps. Over generations, though, the descendants of these pioneers might regard our gravity as impossibly weak, their new normal etched into their very bones. The deeper question isn't just whether we can adapt, it's whether we'd still recognize ourselves afterward. Gas giants demand more than new technology, they demand a redefinition of human resilience. Whether through genetics, machines, or sheer stubbornness, cracking this challenge wouldn't just open a new world to explore, it would reveal what we're capable of when the universe refuses to bend to our will. Picture a farm unlike anything on Earth: no soil, no sunlight, just vast floating greenhouses drifting in the eternal twilight of a gas giant's upper atmosphere. Here, food production wouldn't rely on traditional agriculture, but on radical innovations like hydroponic towers fed by nutrient-rich mist or bioreactors growing protein from cultured cells. The challenge: replicating Earth's ecosystems in a place where a single storm could shred crops like confetti, and where gravity itself makes every drop of water behave unpredictably. Yet, if we crack this puzzle, the rewards could be staggering. Self-sustaining cities harvesting endless harvests from the clouds. Hydroponics would likely be the first frontier. On Earth, these soil-free systems already grow crops in confined spaces using mineral-infused water. But in a gas giant's atmosphere, they'd need to operate in 3 dimensions, with root systems suspended in floating nutrient grids shielded from corrosive gases. Imagine spiraling farms built like jellyfish tentacles, their delicate tendrils absorbing nutrients from the surrounding atmosphere while filters scrub out toxic ammonia or sulfur compounds. The plants themselves might require genetic tweaks to thrive in low light, perhaps borrowing traits from deep-sea organisms that flourish without photosynthesis. Synthetic biology could take things further. Instead of growing plants, why engineer microorganisms directly tailored to the gas giant's environment? Scientists are already experimenting with bacteria that produce edible proteins from hydrogen and carbon dioxide, a process that could be supercharged in a hydrogen-rich atmosphere. These microbial farms might resemble vast floating vats, their contents churning out nutrient-dense slurries or even structured meats without a single blade of grass. The real magic: these organisms could evolve alongside the habitat, adapting to atmospheric shifts faster than any crop cycle. But the most intriguing possibility isn't farming at all, it's foraging. Gas giants might already host native life forms drifting like cosmic plankton in the upper layers. If such organisms exist, they could be harvested or even domesticated, providing a ready-made food source. Picture sky whales: colossal, hydrogen-filled creatures filtering ammonia clouds for nutrients, their biochemistry so alien that processing them into food would require entirely new culinary sciences. Or think of floating algal blooms, their cells rich in exotic lipids, waiting to be skimmed like cream from a planetary-scale ocean. The energy balance is just as critical. Traditional farming consumes vast resources, but in a gas giant, the same storms that threaten stability could power production. Vertical wind turbines might energize grow lights, while thermal gradients run refrigeration units to preserve harvest. Waste there'd be none. Every byproduct from CO2 exhaled by inhabitants to organic refuse would be recycled into the system, creating a closed loop where even bacteria play their part in the food chain. Yet the greatest hurdle might be cultural. Humans have tied food to land for millennia: the smell of soil, the rhythm of seasons. In a sky-bound colony, meals could become utilitarian, divorced from traditions that define our relationship with eating. Would floating cities develop entirely new cuisines, their flavors shaped by the metallic tang of hydrogen-fixed proteins or the umami of ammonia-tolerant fungi? The psychology of dining matters as much as the science, because comfort foods might be the glue holding a civilization together when the ground beneath your feet is just an illusion. This isn't just about survival, it's about redefining what food means in a universe far stranger than our ancestors ever dreamed. Whether through engineered crops, synthetic biology, or harvesting the skies themselves, a gas giant's bounty would demand creativity as vast as the storms that surround it. And if we succeed, the ultimate irony awaits. A civilization that conquers the heavens might just do it one bite at a time. Radiation on Earth is something we can mostly ignore thanks to our planet's thick atmosphere and magnetic shield. But step into the realm of a gas giant, and you're staring down a cosmic firing squad. Jupiter's radiation belts are so intense they deliver a lethal dose to an unshielded human in minutes, bombarding anything in their path with charged particles moving at near light speed. These aren't just background hazards, they're deal breakers for long-term survival. So how could a civilization endure in an environment where the very air crackles with invisible death? The first line of defense might sound like something from a starship's playbook: artificial magnetic fields. Earth's magnetosphere deflects solar radiation like an invisible umbrella, and replicating that on a smaller scale could carve out safe zones within the chaos. Superconducting coils, cooled to near absolute zero, might generate localized shields strong enough to redirect particle streams away from habitats, the catch. Powering such a system would demand staggering energy inputs, likely requiring those same fusion reactors we'd need for survival. And any failure would be catastrophic, leaving inhabitants exposed to a radiation bath with no warning. A subtler strategy involves playing hide and seek with the planet itself. Gas giants' radiation isn't uniformly distributed. It clusters in specific belts, often aligned with magnetic poles. By positioning floating cities in equatorial zones or between layers where the magnetic field naturally weakens, we might find pockets of relative calm. Think of it as building a village in the shadow of a mountain to avoid avalanches, except here, the mountain is a planet-sized force field, and the avalanches are waves of subatomic shrapnel. Then there's the brute force approach: sheer mass, thick walls of hydrogen-rich polymers or water. A surprisingly effective radiation absorber could encase habitats like lead-lined bunkers. Water shields have already been proposed for Mars missions, but scaling them to protect entire cities would mean engineering walls meters thick, turning structures into swimming pools with living quarters inside. Not exactly practical for buoyant habitats where weight is the enemy. Unless we get creative, what if the shielding wasn't static but dynamic? Clouds of charged nanoparticles, suspended in a magnetic mesh around the habitat, could condense into protective barriers when radiation spikes, then dissipate to save weight during quieter periods. Nature might have already solved this puzzle. Earth's extremophiles include bacteria like Deinococcus radiodurans, which shrugs off radiation levels that would vaporize most life. Genetic engineering could borrow their DNA repair mechanisms, crafting humans or crops that tolerate higher doses. Or go further, synthetic biology might design organisms that metabolize radiation, turning a lethal threat into a food source. Imagine forests of bioengineered radiation vines sprouting from habitat walls, their leaves dark with pigments that convert particle strikes into stored energy. The irony is profound. Gas giants' radiation belts aren't just obstacles, they're fingerprints of the planet's raw power. Tapping that energy while evading its lethality would require a dance of precision and audacity, where the difference between survival and annihilation hinges on forces we're only beginning to understand. But if we master this balancing act, the reward isn't just safety, it's proof that even the universe's deadliest traps can be outmaneuvered. Living in a gas giant's atmosphere would turn every commute into a high-stakes odyssey, where rush hour means navigating hurricane-force winds and dodging lightning storms the size of continents. Unlike Earth, where roads and rails tether us to solid ground, a floating city here would need to master the art of movement in a realm with no fixed points, where the very concept of stationary is up for debate. So how do you anchor a metropolis when the ground beneath you is a supersonic river of gas? One answer might lie in dirigibles, not the quaint airships of Earth's past, but colossal, AI-piloted behemoths designed to ride atmospheric currents like leaves on a river. Picture a city suspended beneath a hydrogen-filled envelope, its shape dynamically adjusting to minimize wind resistance while internal ballast systems fine-tune buoyancy. These wouldn't be passive balloons, they'd be active navigators using predictive algorithms to anticipate wind shear and thermal updrafts, subtly shifting altitude to exploit stable layers. The challenge: gas giants don't have predictable jet streams like Earth. Their storms are capricious, often lasting centuries but shifting direction without warning. A single miscalculation could send a habitat spiraling into a storm cell where pressures would crumple it like paper. Then there's the sci-fi dream: anti-gravity. While purely speculative, breakthroughs in quantum physics or exotic matter could one day allow structures to hover independent of atmospheric density, effectively ignoring the chaos below. Imagine platforms stabilized by counteracting gravitational forces with precisely tuned energy fields, creating pockets of calm amid the tempest. The catch: we're centuries away from such tech, if it's even possible. For now, engineers might hedge their bets with hybrid systems, combining buoyant materials with electromagnetic repulsion to reduce reliance on the atmosphere's mercy. A more pragmatic approach: embrace the chaos. Gas giants are perpetual motion machines, their winds forming colossal, stable bands between chaotic storms. Habitats could sail these currents, using deployable fins or plasma actuators, devices that ionize surrounding gas to create steerable thrust to maintain position. The trick would be balancing mobility with stability. A city needs to drift enough to avoid destruction, but not so much that it loses contact with vital infrastructure like mining drones or energy harvesters. Think of it as cosmic Parker, where survival depends on reading the environment faster than it can change. Of course, the real nightmare is storms. Jupiter's great red spot eats Earth-sized hurricanes for breakfast, and its smaller cousins roil the atmosphere with winds exceeding 600 kilometers per hour. Traditional anchors are useless here. No cable could withstand that punishment. Instead, habitats might deploy storm parachutes, massive drag chutes designed to stabilize against gusts by increasing atmospheric resistance, or use centrifugal force, spinning sections of the city to generate artificial stability. Alternatively, they could adopt the ultimate defensive strategy: dive. Temporary descents into denser atmospheric layers might offer shelter from the worst winds, though the pressure and heat trade-offs would require habitats built like deep-sea submersibles. The wild card: bio-inspired solutions. Nature already thrives in fluid environments. Consider jellyfish, which pulse through ocean currents with minimal energy. Gas giant cities might mimic these organisms, using flexible, undulating structures to swim through the atmosphere, or even form symbiotic relationships with native life if it exists, hitching rides on colossal floating organisms like cosmic remoras clinging to whales. The paradox of gas giant navigation is that mobility equals survival. A city that can't adapt to shifting winds isn't just inconvenienced, it's doomed. Future engineers won't just be building habitats, they'll be crafting ecosystems of motion, where every storm avoided is a victory and every current ridden is a free ticket to another day. It's a reminder that in the universe's most hostile places, staying alive means never staying still. Staying connected in the swirling depths of a gas giant isn't just about sending a quick message home. It's about fighting through an atmosphere that eats radio waves for breakfast. Imagine shouting into a hurricane while submerged in a swimming pool filled with liquid metal, and you'll start to grasp the challenge. The same dense layers of hydrogen, helium, and exotic compounds that make these planets so visually stunning also act like a cosmic Faraday cage, absorbing or scattering most electromagnetic signals before they can escape. Traditional radio communication would be hopeless, vanishing into the noise of atmospheric static or dissolving under the crushing pressure. So how does a floating city talk to the outside universe without resorting to messenger drones or cosmic semaphore? One solution might lie in relay stations, floating beacons positioned high above the worst of the atmospheric interference. Picture a network of buoyant satellites, tethered to the city below but hovering near the upper cloud layers where the air thins enough for signals to punch through. These relays could act like celestial switchboards, bouncing messages between the depths and orbiters overhead using tight beam lasers or ultra-high-frequency radio waves. The tech isn't entirely speculative. NASA Juno probe managed to transmit data from Jupiter by aiming its antenna precisely at Earth during brief atmospheric lulls. Scale that up and you've got a lifeline, albeit one constantly battling the planet's tantrums. But why fight the atmosphere when you could exploit it? Acoustic communication, normally useless in space, might find new life here. Sound travels far more efficiently through dense gases than through the vacuum, and certain low-frequency waves could theoretically propagate for thousands of kilometers without scattering. A city might encode data in pulses of infrasound, inaudible to human ears but detectable by sensitive receivers on orbiting platforms. The drawback: speed. Even at Mach speeds, sound waves would take hours to traverse the planet's girth, making real-time chats with Earth impossible. For urgent messages, we'd need something faster, much faster. Enter quantum entanglement, the holy grail of instant communication. While still in its infancy, quantum networks rely on paired particles that remain mysteriously linked across vast distances, changing states in perfect sync. If perfected, this tech could enable lag-free messaging, bypassing the atmosphere entirely by transmitting information through what Einstein called spooky action at a distance. The catch: entanglement is fragile, easily broken by interference, and we'd need to establish and maintain a chain of quantum repeaters stretching from the gas giant's depths to Earth, a feat requiring breakthroughs we can barely envision today. Then there's the brute force alternative: physical data vaults. In a world where signals struggle, why not send information the old-fashioned way by carrying it? Automated drones, armored against the atmosphere's wrath, could shuttle memory crystals packed with terabytes of data to orbital way stations. These data mules would be slower than light-speed signals but far more reliable, acting like interstellar postmen braving the storm. Picture a fleet of sleek, heat-shielded couriers darting between the clouds and space, their cargo holds stuffed with everything from scientific findings to birthday messages from homesick colonists. The wild card: native infrastructure. If gas giants harbor even simple life forms, their biology might inspire new solutions. Imagine organisms that naturally generate bioluminescent pulses or electromagnetic fields, signals we could co-opt or amplify into a planetary-scale network. Or consider the planet's own magnetic fields, which might be harnessed to encode data in ripples of energy, turning Jupiter into a colossal hard drive. The deeper truth is that communication here isn't just about technology, it's about redefining connection itself. A civilization in the clouds wouldn't just tolerate delays or static. It would build a culture around them where patience and redundancy are baked into daily life. Messages might be sent in triplicate, stamped with timestamps accounting for atmospheric turbulence, or even artistically encoded to survive degradation. The very concept of live communication could become nostalgic, a relic of Earth's gentle skies. Yet for all the challenges, the reward is profound, proof that even in the universe's most isolated corners, no one is truly alone. Think about the most valuable real estate in the solar system, not on Mars or the Moon, but suspended in the violent skies of a gas giant. The reasons to live here wouldn't just be about survival, they'd be about profit, discovery, and industries we can barely fathom today. Mining would be the first frontier. Gas giants are cosmic treasure troves, their atmospheres laced with helium-3, an isotope rare on Earth but abundant in these swirling giants. On our planet, helium-3 is the stuff of fusion dreams, a potent fuel that could power civilizations without radioactive waste. Harvesting it from Jupiter's clouds would be like striking oil in an endless desert, except the desert is a hurricane, and the rigs are floating factories buffeted by supersonic winds. The process wouldn't be pretty. Imagine massive, balloon-like refineries trailing miles of magnetic scoops, filtering isotopes from the hydrogen soup while dodging lightning strikes. The payoff, a fuel so dense in energy, a single cargo load could power cities for years. But mining is just the beginning. Tourism in a gas giant would make Everest expeditions look like playground outings. Picture luxury observation decks dangling from the edges of floating habitats, where billionaires sip cocktails while watching storms large enough to swallow Earth rage below. The bragging rights alone, I vacationed inside Jupiter's Great Red Spot, would command prices that dwarf space station getaways. Of course, the logistics are absurd. Shuttle flights would need to navigate radiation belts and atmospheric shear that could shred conventional spacecraft. But for those with the money and the madness, it might just be the ultimate adrenaline rush. Then there's science. Gas giants are cosmic laboratories, their extreme pressures and temperatures creating states of matter impossible to replicate on Earth. Researchers would pay anything to study metallic hydrogen up close, a material that might revolutionize superconductors or propulsion systems. Or consider the hunt for alien life. If bioluminescent microbes drift in those clouds, their biology could redefine our understanding of life itself. Universities and corporations might fund floating research stations, their instruments probing deeper into the planet's layers than any probe ever could. But here's the catch: none of this works without staggering upfront investment. The infrastructure to mine, house, and transport people in this hellscape would cost trillions with no guarantee of returns. Private companies might balk at the risk, leaving it to governments or megacorporations with patience deeper than Jupiter's gravity well. And even if the tech matures, there's the ethical question: should we industrialize worlds that might already harbor life? Strip mining a gas giant could be like turning the Amazon into a parking lot, except we'd never know what we destroyed. The irony: the same forces that make gas giants so hostile also make them invaluable. Their storms clean the atmosphere of debris, their gravity shields inner planets from asteroids, and their composition holds clues to the solar system's birth. Exploiting them might fund humanity's future, but preserving them could answer questions we haven't even thought to ask. The real industry here isn't just about profit, it's about balancing greed with wonder and deciding whether some frontiers are worth crossing at all. Floating cities inside gas giants wouldn't just challenge engineering, they'd rewrite the rules of human society from scratch. Picture thousands of people crammed into pressurized bubbles, suspended in perpetual twilight, where a single hull breach could mean catastrophe. In environments this fragile, social order wouldn't be about convenience, it'd be a matter of life and death. The result: communities might evolve into something unrecognizable compared to Earth's nations, shaped by unrelenting pressure to cooperate or face extinction. One possibility leans toward extreme collectivism. When every breath depends on shared air filters and every meal comes from communal algae vats, individualism could become a luxury no one can afford. Cities might function like high-tech beehives, with citizens assigned roles based on aptitude: atmospheric technicians, radiation shield specialists, storm pattern analysts, all working under strict resource quotas. Personal possessions would be minimal when cubic meters of living space are more precious than gold, and decision-making could shift toward meritocratic councils where survival expertise trumps popularity. These wouldn't be dictatorships so much as hyper-efficient cooperatives where slacking off endangers everyone. The closest Earth analog, perhaps submarine crews or Antarctic research stations amplified to planetary scale. But history warns us that isolation breeds control. The constant threat of disaster could justify draconian oversight monitoring systems tracking oxygen consumption, movement restrictions during magnetic storms, mandatory genetic screenings to prevent mutations from radiation exposure. A gas giant's relentless hostility might foster societies where safety trumps freedom, with AIs or oligarchies making decisions too risky to put to vote. Imagine neighborhoods patrolled by drones scanning for waste infractions, or childbirth permits tied to habitat capacity. The irony: these could be genuinely benevolent autocracies, their leaders believing absolute control is the only way to prevent a cascade failure that dooms everyone. Yet there's another path, one carved by necessity rather than force. Floating cities might develop radical decentralization, where neighborhoods operate as self-sufficient pods to minimize single points of failure. Governance could resemble swarm intelligence, with each district negotiating resource trades through blockchain-like systems while maintaining autonomy over local affairs. In a world where traditional laws can't anticipate every atmospheric crisis, adaptive micro-societies might outperform rigid hierarchies. Picture a culture where reputation currency matters more than money. Your survival depends on neighbors vouching for you during evacuation drills, making social capital literal life insurance. The wild card: how humans psychologically adapt to endless confinement. On Earth, we derive comfort from horizons, seasons, and open spaces. Gas giant dwellers might develop entirely new social norms to combat sky claustrophobia. Perhaps communal VR gardens simulating Earth's landscapes, or ritualized storm watches where communities bond by observing atmospheric fury together. Art and music could evolve to incorporate the constant hum of habitat machinery, turning necessity into aesthetic. Over generations, citizens might even develop neurobiological differences, their brains wired to find comfort in the hum of air recyclers the way we crave birdsong. The most fascinating variable isn't governance but identity. Isolated for centuries, floating cities could diverge into distinct cultures as varied as Earth's nations, except shaped not by geography but by atmospheric quirks. A metropolis riding Jupiter's equatorial jet stream might value speed and adaptability, its language peppered with wind pattern slang. Another drifting in Saturn's polar hexagon could revere stability, its architecture built to withstand 60-year storm cycles. These wouldn't just be societies living in gas giants, they'd become societies of the gas giants, as inseparable from their environment as islanders from the sea. The ultimate lesson: extreme worlds don't just test technology, they stress test humanity itself. Whether these cities become oppressive silos or vibrant experiments in cooperation depends less on the storms outside than the choices we make about who we become inside. And that answer won't be found in any engineering schematic, but in the fragile, stubborn thing we call human nature. Jupiter isn't just a planet, it's a cosmic titan, a laboratory of extremes where every rule of habitability gets twisted into something unrecognizable. Let's put all those wild theories about gas giant civilizations to the test here, because if humanity could make it on Jupiter, we could make it anywhere. Start with scale. This beast could swallow 1,300 Earths with room to spare, its atmosphere stretching over 5,000 kilometers deep before transitioning into liquid metallic hydrogen. Those swirling bands of cream and ochre aren't just pretty, they're continent-sized rivers of gas flowing at speeds that'd make supersonic jets look sluggish. And then there's the Great Red Spot, a storm so vast it's been devouring smaller hurricanes for centuries, its winds screaming at 430 kilometers per hour. This isn't just weather, it's planetary fury written in cloud vortices larger than our entire planet. Now imagine trying to park a floating city in that chaos. The first hurdle: Jupiter's rotation. A day here lasts just under 10 hours, whipping its atmosphere into a frenzied Coriolis effect that shreds any structure not designed to flex like a reed. Stability would require habitats to either match the planet's spin with precision or anchor themselves too well, nothing. There's no ground to tether to, no bedrock to drill into. One speculative solution involves aerostat habitats riding the boundary between ammonia ice clouds and the stratosphere below, where winds might be marginally less apocalyptic. Picture a city suspended by helium-filled envelopes, its foundations reinforced with materials that flex like cartilage under pressure, dissipating stress instead of resisting it. But Jupiter's real party trick is its magnetic field. This isn't just a planetary magnet, it's a monster 14 times stronger than Earth's, churned into existence by the planet's spinning metallic hydrogen core. The radiation belts it generates are lethal enough to fry unshielded electronics in hours, bathing anything near the equatorial zones in a constant hail of charged particles. A civilization here would need habitats wrapped in meters-thick water shielding, or more likely buried deep enough in the atmosphere to let the gas itself absorb the worst of the radiation. That means living under hundreds of kilometers of opaque, crushing hydrogen, where sunlight never reaches and the only illumination comes from artificial lights or the eerie glow of auroras crackling along magnetic field lines. Yet within this catalogue of horrors lie opportunities. Jupiter's internal heat pumps out more energy than it receives from the sun, creating thermal gradients that could power fusion reactors or Stirling engines on an industrial scale. The upper cloud decks brim with helium-3, a potential fusion fuel so rare on Earth that mining it here could justify the entire enterprise. And then there's the atmosphere itself, a chemist's playground where exotic molecules like ammonium hydrosulfide form under pressures that turn hydrogen into a supercritical fluid. Factories floating in the sweet spot between crushing depth and radiation hell could synthesize materials impossible to manufacture anywhere else in the solar system. The wildest possibility, Jupiter might already be inhabited, not by cities but by life forms as alien as the planet itself. Astrobiologists speculate about organisms floating in droplet-like membranes, harvesting chemical energy from updrafts or even feeding on charged particles in the radiation belts. Finding them would require probes that could hover for years in the habitable zone, a layer around 50 to 100 kilometers down, where temperatures and pressures approach Earth like ranges. If such life exists, it wouldn't just redefine biology. It'd force us to ask whether building cities here would make us pioneers or invasive species. Jupiter doesn't just defy human colonization, it mocks it. Every rule we've ever learned about survival gets rewritten here, where the sky is an ocean, the ground is a myth, and the very air crackles with enough energy to vaporize steel. Yet that's precisely why it fascinates. Conquering this world wouldn't be about bending it to our will, it'd be about learning to speak its language, to dance with storms instead of fleeing them. The day we crack that code, the solar system stops being a collection of rocks and becomes something far grander, an endless frontier waiting in the clouds. If Jupiter is the solar system's bruiser, all muscle and fury, then Saturn is its elegant cousin, hiding formidable power beneath breathtaking beauty. With gravity just slightly stronger than Earth's, floating cities here wouldn't face the same crushing forces as on Jupiter, making mobility and structural integrity marginally less impossible. But Saturn's real ace, those rings, stretching 280,000 kilometers wide yet barely thicker than a skyscraper is tall, they're not just celestial jewelry, they're a floating hardware store of water ice, rocky debris, and organic compounds, orbiting within easy reach of hypothetical skyborne metropolises. The storms here, while still monstrous by Earth standards, are curiously subdued compared to Jupiter's never-ending tantrums. Saturn's hexagonal polar vortex, a six-sided jet stream wider than 2 Earths, is more geometric oddity than Death Trap, with winds only hitting 350 kilometers per hour. Upper atmosphere currents move at a comparatively leisurely 1,600 kilometers per hour, half Jupiter's fury. For floating habitats, that's the difference between weathering a Category 5 hurricane and a Category 3 still brutal, but potentially survivable with dynamic stabilization systems. Temperature gradients are less extreme too, with cloud tops hovering around -180 degrees Celsius and inner layers reaching a balmy 8,000 degrees, still hellish, but a cooler hell than Jupiter's 20,000-degree core inferno. Now consider Saturn's secret weapon, moons. Enceladus spews geysers of water vapor from a subsurface ocean. Titan's methane lakes mirror Earth's hydrologic cycle, and even tiny Hyperion resembles a cosmic sponge, its porous surface hinting at vast ice reserves. These aren't just scientific curiosities, they're potential supply depots for floating cities. Ice mining drones could shuttle between Enceladus plumes and orbital processing plants, converting frozen water into breathable oxygen and hydrogen fuel. Titan's hydrocarbon seas might feed chemical reactors producing plastics or synthetic fuels, while its nitrogen-rich atmosphere could replenish habitat air supplies. The logistics would be daunting: moon bases connected to cloud cities by fragile supply chains spanning hundreds of thousands of kilometers. But unlike Jupiter's resource-starved abyss, Saturn's system offers raw materials within relatively easy reach. Yet Saturn has its own nightmares. The planet's magnetic field, though weaker than Jupiter's, still generates intense radiation belts, especially near the rings where charged particles get trapped like flies in a web. And those stunning rings, they're a double-edged sword. Millions of icy fragments traveling at orbital speeds could shred unprotected habitats like buckshot. Any city floating near the ring plane would need electromagnetic deflectors or armored skirts, turning aesthetic dazzle into an engineering headache. The wild card here isn't technology, it's biology. Saturn's upper atmosphere hosts unexplained great white spots, massive storm systems that erupt every few decades, possibly fueled by water vapor from ring particles raining down. Some astrobiologists speculate these transient oases of moisture could harbor microbial life adapted to ephemeral wet zones. If true, floating cities might not just mine the rings, they could accidentally contaminate them, triggering ecological disasters we wouldn't notice until it was too late. What emerges is a tantalizing paradox. Saturn offers gentler physics but more complex logistics, breathtaking resources paired with fragile ecosystems. Where Jupiter demands we reinvent survival, Saturn asks us to master cosmic supply chains and decide whether exploiting this pristine system is worth the price. The rings may glitter with opportunity, but they also hold up a mirror, forcing us to confront what kind of interstellar civilization we want to become. Leaving behind the violent splendor of Jupiter and Saturn, the ice giants Uranus and Neptune present a radically different vision for gas giant habitation, one where the chaos of endless storms gives way to an eerie, frozen stillness. These distant worlds, often overshadowed by their flashier siblings, operate by their own rules. With atmospheres rich in methane, water, and ammonia ices, they're more like cosmic freezers than the pressure cookers of the solar systems in a giant. But don't let the quieter skies fool you. What they lack in visible fury, they make up for in mysteries that could rewrite the playbook for off-world colonization. The first surprise, weather or the lack thereof. Compared to Jupiter's ceaseless maelstroms, Uranus and Neptune seem almost serene. Upper winds top out at a gentle 900 kilometers per hour, still enough to fling cars into orbit, but a far cry from the supersonic tempests next door. Even Neptune's great dark spot, while formidable, is a transient feature rather than a permanent scar like Jupiter's great red spot. For floating cities, this could mean less energy spent on stormproofing and more on sustainability. Picture habitats gliding through Neptune's methane haze like Arctic research stations adrift in a planetary-scale blizzard, their outer shells coated in ice-resistant alloys to prevent buildup from the frozen atmosphere. But calm comes at a cost: energy scarcity. Jupiter and Saturn radiate internal heat from gravitational compression and radioactive decay, offering exploitable thermal gradients. Uranus, by contrast, is a cosmic anomaly. Its core barely emits more heat than it receives from the distant sun, leaving its atmosphere a frigid -220 degrees Celsius with few natural energy sources. Neptune fares slightly better, its faint internal warmth powering sluggish atmospheric circulation, but neither holds a candle to the energy bonanza of their larger cousins. Colonies here would need to get creative, perhaps relying on nuclear fission or beamed solar power from orbital mirrors, turning these dim realms into artificial oases. Then there's the composition. Unlike hydrogen-dominated Jupiter and Saturn, ice giants are packed with heavy volatiles, water, ammonia, and methane churned into slushy mantles beneath their outer gas layers. This cocktail could be a gold mine for industrial chemistry. Methane might be cracked for hydrogen fuel, ammonia refined into fertilizers for hydroponic farms, and water ice mined from deep atmospheric layers where pressures solidify it into exotic forms. The catch: accessing these resources means diving into regions where pressures exceed 1,000 atmospheres and temperatures swing from cryogenic to furnace hot in narrow bands. Robotic drones built like deep-sea submersibles might brave these layers, their hulls reinforced with boron nitride ceramics to withstand conditions that would crumple conventional probes. Magnetic fields add another twist. Uranus's field is a drunken mess, tilted 60 degrees from its axis and offset from the planet's center, while Neptune's wobbles unpredictably. These erratic fields would play havoc with navigation and communication, disrupting compasses and scattering radio signals. Habitats might need to rely on acoustic beacons or quantum-linked positioning systems, turning each city into a self-contained network navigating by planetary vibrations rather than stars. The wild card: seasons. Uranus rolls around the sun like a wayward billiard ball, its 98-degree axial tilt giving each pole 42 years of continuous sunlight followed by 42 years of darkness. Colonies here would face cycles of endless twilight and perpetual night, demanding artificial circadian rhythms to prevent psychological collapse. Neptune's more moderate tilt offers stable seasons, but with sunlight 900 times dimmer than Earth's, photosynthesis is off the table. Food production would depend entirely on synthetic biology: algae vats tuned to metabolize methane or bacteria engineered to thrive on atmospheric trace elements. What emerges is a paradox. Ice giants offer sanctuaries from the storm but demand sacrifices in warmth and energy. Their quieter skies might cradle humanity's most isolated outposts, cities suspended in twilight like jewels in the void. Yet for all their challenges, they hold one irresistible lure: the chance to study planetary extremes we've barely begun to understand. Uranus's buried oceans of supersonic water or Neptune's diamond rain aren't just curiosities, they're glimpses into the universe's most alien physics. Tapping those secrets wouldn't just sustain a civilization, it could redefine it. The lesson: habitability isn't just about finding Earth-like conditions. It's about adapting to the universe's indifference, whether in the eye of the storm or the heart of the freeze. And if ice giants teach us anything, it's that survival doesn't always mean comfort. Sometimes it means learning to love the cold. The possibility of life inside a gas giant isn't just science fiction, it's a scientific frontier that forces us to rethink everything we know about biology. Forget the familiar green hills and blue oceans of Earth. Imagine creatures shaped by perpetual storms, organisms that breathe hydrogen instead of oxygen, and life forms that float like cosmic jellyfish in an endless sky. The idea seems outrageous until you consider how life on Earth clings to the most hostile corners of our planet. Deep-sea vents, acidic hot springs, even the vacuum of space aboard the International Space Station. If life can thrive there, why not in the dense, turbulent atmospheres of Jupiter or Saturn? One compelling theory revolves around ammonia-based life. On Earth, water is the universal solvent, the medium in which all known biochemical reactions occur. But in the freezing upper layers of a gas giant, water would be locked in ice, useless for life as we know it. Enter ammonia. At certain pressures and temperatures, ammonia remains liquid where water would freeze, opening the door to biochemistry that swaps H2O for NH3. Picture cells with membranes made of nitrogen-rich compounds instead of lipids. Their metabolic pathways tuned to extract energy from chemical reactions we'd consider toxic, like converting acetylene and hydrogen sulfide into usable fuel. These wouldn't be simple microbes necessarily. Some models suggest ammonia-based life could evolve complexity akin to Earth's plants or even filter feeders, drifting through the clouds in vast, invisible herds. Then there's the concept of aerial plankton organisms that treat a gas giant's atmosphere like an ocean. Earth's seas teem with microscopic life that floats on currents, and the same principle could apply in the dense hydrogen skies of Jupiter or Saturn. These creatures might resemble Earth's radiolaria, delicate, glass-like structures filled with buoyant gases, or even balloon-like organisms that rise and fall through atmospheric layers, harvesting chemical energy from lightning discharges or ultraviolet light filtering through the upper clouds. Some astrobiologists speculate they could form vast, living nets, their interconnected filaments stretching for kilometers to trap nutrients suspended in the winds. The wildest idea, creatures that treat radiation as a food source. Jupiter's magnetosphere is a death trap for humans, but for an organism evolved to harness charged particles, it could be an all-you-can-eat buffet. Imagine life forms with organic superconductors woven into their biology, channeling the planet's relentless radiation into usable energy like living nuclear reactors. Their bodies might glow with eerie bioluminescence, a byproduct of metabolizing particles that would kill unadapted life in seconds. The challenge, of course, is detecting such life. Gas giants don't offer surfaces to land on or lakes to sample. Any search would require probes capable of hovering in the habitable zones layers where temperature and pressure allow for liquid solvents, and sniffing the atmosphere for metabolic byproducts like phosphine, which on Earth is produced by anaerobic bacteria. The irony is rich. We might discover life not by seeing it, but by catching the chemical whispers of its existence in the winds. But here's the mind-bending twist. If life exists there, it wouldn't just be alien in form. It would redefine the very meaning of planet. Gas giants might not be barren wastelands but vibrant biospheres, their ecosystems hidden behind veils of storm and gas. And if that's true, the universe could be teeming with life in places we once dismissed as hellscapes. The lesson isn't just about gas giants, it's about humility. Life, it seems, doesn't care about our assumptions. It finds a way, even in the last places we'd think to look. Humanity has always been driven by a restless urge to push beyond the horizon, whether sailing uncharted oceans or launching rockets into the void. But the idea of colonizing a gas giant isn't just about exploration, it's about survival. Earth's resources are finite, and with the global population expected to near 10 billion by mid-century, the strain on our planet's ecosystems is reaching a breaking point. Freshwater reserves are dwindling, arable land is eroding, and the race for rare minerals fuels geopolitical tensions. Against this backdrop, gas giants start to look less like cosmic curiosities and more like potential lifelines. Their atmospheres contain vast reserves of hydrogen, helium, and other volatiles, elements crucial for fusion energy, industrial processes, and even breathable air if extracted and processed. The promise of near-limitless resources could transform these turbulent worlds into the oil fields of the future, fueling not just colonies but entire interplanetary economies. Yet resource scarcity is only part of the equation. There's also the looming specter of planetary catastrophe, asteroid impacts, supervolcanoes, or climate collapse threats that could render Earth uninhabitable in centuries or even decades. Gas giants offer a grim but compelling insurance policy. Their sheer size and distance from the inner solar system could make them refuges when terrestrial planets falter. Imagine our colonies floating in Saturn's upper clouds, their inhabitants watching from afar as Earth's biosphere buckles under an extinction-level event. The dystopian irony is hard to ignore: humanity fleeing a ruined world only to shack up inside a planet where the very air is poison. But not all motivations are born of desperation. Scientific curiosity might be the purest driver of all. Gas giants are living laboratories of extreme physics, their interiors hiding states of matter that defy replication on Earth. Metallic hydrogen, diamond rain, and superionic water, these aren't just theoretical oddities. They could hold the keys to revolutionary technologies, from room temperature superconductors to propulsion systems that slash interstellar travel times. Establishing permanent research outposts in those hostile skies would grant unprecedented access to these phenomena, turning Jupiter's storms or Neptune's icy depths into testing grounds for the next century's breakthroughs. The ethical dilemmas, though, are inescapable. Is it reckless to pour trillions into settling an environment where a single engineering failure could wipe out thousands? Should we prioritize fixing Earth's problems over gambling on untamed worlds? And what if gas giants already harbor life microbes or even complex organisms drifting unseen in their depths? Colonization could amount to an interstellar invasion, disrupting ecosystems we don't yet understand. The debate echoes historic crossroads. Like settlers who crossed oceans only to displace indigenous cultures, we might repeat old mistakes on a cosmic scale. Ultimately, the drive to inhabit gas giants isn't just about practicality, it's about legacy. Whether fueled by fear, greed, or wonder, the attempt would redefine what it means to be a spacefaring species. Succeed and humanity becomes something new, creatures unshackled from terrestrial limits, capable of thriving in the universe's most unforgiving corners. Fail, and the lesson might be equally profound: that some frontiers, no matter how alluring, were never meant to be ours. Building a civilization inside a gas giant isn't just an engineering challenge, it's a gauntlet thrown at the feet of science itself. The technologies required to make this vision possible don't just need to be groundbreaking, they'd need to rewrite the rulebook of human capability. Start with material science, the very foundation of survival in an environment where the air crushes like an ocean and shreds like a hurricane. Today's strongest alloys would crumple under gas giant pressures faster than aluminum foil in a vise. What we'd need are materials with properties that border on magic, metamaterials that flex like rubber but resist deformation like diamond, or self-healing polymers that seal breaches before corrosive gases can exploit them. Imagine building with substances inspired by deep-sea organisms, materials that actually grow stronger under pressure, their molecular structures tightening rather than fracturing. We're glimpsing early versions of this with carbon nanomaterials and metallic glasses, but the leap from lab curiosities to planetary-scale construction materials is staggering. Even graphene, 200 times stronger than steel, would need revolutionary reinforcement to handle millennia of unrelenting atmospheric abuse. Power is another Everest to climb. Solar energy is useless beneath hundreds of kilometers of opaque clouds, and chemical batteries would be laughably inadequate for cities measured in megatonnage. Fusion power isn't just preferable here, it's non-negotiable. Gas giants offer a silver lining. Their atmospheres are essentially endless reservoirs of hydrogen, the very fuel fusion reactors crave. But current fusion tech is like trying to start a campfire with wet matches. We've achieved brief moments of ignition, but sustaining a stable reaction that outputs more energy than it consumes remains elusive. The difference between today's experimental tokamaks and the reactors needed to power a floating metropolis is like comparing a paper airplane to a stealth bomber. We'd need compact, self-regulating fusion plants that can operate autonomously for decades, all while riding atmospheric currents that could shake them apart. The progress is promising. Private ventures and international projects like ITER inching closer to net positive reactions. but commercial viability is still decades away at best. Then there's the brain of the operation, artificial intelligence. Maintaining a floating city in a gas giant would be like performing heart surgery while skydiving through a tornado. Every system would require constant, hyper-precise adjustments. Human crews couldn't possibly react fast enough to atmospheric microbursts or radiation spikes measured in milliseconds. Instead, we'd need AI overseers with advanced predictive capabilities, algorithms trained on planetary fluid dynamics to anticipate storms before they form, and robotic repair swarms that can rebuild damaged structures mid-gale. Current machine learning is impressive, but brittle chatbots hallucinate facts, and self-driving cars still get confused by rain. The AI for gas giant habitation would need the creativity to improvise solutions to never-before-seen problems and the reliability to never, ever crash. We're talking about systems that make today's most advanced drones look like pocket calculators capable of managing millions of data points per second while orchestrating fleets of maintenance bots across a city that never stops moving. The timeline for these breakthroughs isn't just uncertain, it's a Rorschach test for optimism. Materials strong enough to laugh off gas giant pressures could emerge in 50 years or 500. Fusion might hit its stride by 2050 or remain perpetually 30 years away. An AI capable of running an entire floating civilization could require advances in quantum computing we haven't even imagined yet. But here's the twist: none of these technologies exist in isolation. Progress in one accelerates the others. Room temperature superconductors, another pipe dream today, could revolutionize both fusion containment and magnetic shielding. Advances in nanotechnology might yield both radiation-resistant materials and self-assembling repair drones. The path to gas giant cities isn't a straight line. It's a web of interconnected discoveries, each breakthrough pulling others within reach. What makes this endeavor so fascinating isn't the distance to the goal, but how pursuing it transforms our capabilities along the way. The same technologies that might one day let us float cities in Jupiter's clouds could also solve energy crises, revolutionize medicine, and redefine manufacturing here on Earth. The gas giants aren't just a destination, they're the ultimate crucible for human ingenuity, forcing us to evolve beyond planetary thinkers and become something new. Whether we ever plant flags in those swirling skies is almost beside the point. The trying itself remakes us. Even if we crack the physics of gas giant colonization, we'd still face a moral quagmire, one that forces us to ask whether we should conquer these worlds, not just if we can. Picture this: we build the first floating city in Jupiter's clouds, only to discover microbial life thriving in the ammonia-rich layers below. Suddenly, our triumph feels less like exploration and more like an invasion. The ethical weight here is crushing because gas giants aren't just hostile environments. They might be ecosystems we don't yet understand, teeming with life so alien we'd struggle to recognize it. History offers grim precedents. Earth's colonial past is littered with ecosystems devastated by introduced species and industrial exploitation. Think of rats wiping out island bird populations or rainforests leveled for palm oil. On a gas giant, the stakes are higher. Our mere presence could disrupt atmospheric balances that took eons to stabilize. Mining operations might contaminate chemical cycles critical to native organisms, while waste heat from fusion reactors could trigger unpredictable climate shifts in localized zones. And what if our probes or cities accidentally introduce Earth microbes that outcompete native life? The galaxy's first interplanetary extinction event could happen because we didn't look before we leapt. Yet the counterargument is seductive. What if we're meant to expand? Life's imperative, after all, is to adapt and spread. Gas giants represent resources that could sustain civilization for millennia: helium-3 for clean energy, hydrogen for fuel, rare isotopes for medicine. Denying humanity these tools might condemn us to stagnation on a dying Earth. Some would argue that survival justifies the risk, especially if native life, if it exists, is microbial. We bulldoze bacteria-laden soil for skyscrapers every day on Earth. Why hold gas giants to a higher standard? The middle ground might lie in planetary protection protocols, scaled to gas giants' unique challenges. Robotic scouts could spend decades mapping potential biosignatures before cities are approved, with strict no-go zones around sensitive regions. Mining might be restricted to atmospheric layers deemed sterile, while habitats incorporate closed-loop systems to prevent contamination. But even these measures assume we can define harm in an environment where life might not follow Earth's rules. Is altering Jupiter's storm patterns ethically equivalent to terraforming Mars, or is it more like poisoning a well no one else can drink from? The deepest question isn't about right or wrong, it's about identity. If we become a species that reshapes gas giants, what does that make us, stewards or conquerors? The answer might hinge on humility. Before we claim these worlds, we'd need to listen to them, to learn their rhythms and secrets, because the universe rarely forgives arrogance, and the storms of Jupiter have been practicing their wrath for billions of years. Disaster in a gas giant doesn't mean power outages or leaks, it means annihilation in minutes. Picture this: a habitat's outer shielding fails during a storm surge, and suddenly 600 km/h winds peel back layers like an onion, exposing the city's fragile core to pressures that liquefy steel. The survivors aren't just fighting for resources, they're battling an environment that treats human engineering like tissue paper. In these moments, redundancy isn't a luxury, it's the only thread between life and oblivion. First, consider structural collapse. On Earth, buildings crumble inward or topple sideways when they fail. In a gas giant, structures don't fall, they implode, twist apart, or get shredded mid-air. A breach in a critical support beam could cascade through the entire habitat as atmospheric pressures surge inward like a vise. The response: fractal architecture, designs where every component is self-supporting, able to isolate damage like a lizard shedding its tail. Imagine neighborhoods encased in hexagonal pods, each capable of sealing itself off within milliseconds, trading sacrificed sections to preserve the whole. Rescue here wouldn't mean fire trucks and ambulances, it'd be swarms of repair drones, welding nanofiber patches onto cracks while steering the crippled city toward calmer atmospheric layers. Resource shortages amplify the terror. Earth supply chains stretch across continents, but a floating city's lifelines dangle from orbital elevators or skyhooks that must traverse lethal radiation belts. One missed delivery of hydrogen filters or oxygen scrubbers could choke a population within days. The solution might lie in extreme recycling, synthetic ecosystems where every molecule of waste is reprocessed into food, fuel, or breathable air. Think of composting toilets dialed to cosmic extremes, bacteria engineered to break down plastics into edible proteins, or algae vats tuned to convert exhaled carbon dioxide back into oxygen with near-perfect efficiency. The margin for error, zero. Then there's the ultimate nightmare: getting stranded. If propulsion fails and a habitat drifts into a storm cell or sinks too deep, evacuation isn't an option. No spacecraft could dock in those winds, and no pressure suit could withstand the environment outside. Survival would depend on lifeboat protocols, emergency clusters of reinforced pods designed to detach and ride the storms like cork buoys in a tsunami, their transmitters screaming for help while their occupants huddle in induced hibernation to stretch supplies. Even then, rescue might take years, assuming anyone could pinpoint their signal amid the planet's radio noise. The psychological toll would rewrite human resilience. Earth's disaster survivors cling to hope of daylight, open air, solid ground. Gas giant refugees have none of that, just the eternal howl of wind and the crushing weight of an atmosphere that wants to erase them. Social order could shatter into tribalism, with factions fighting over air filters, or solidify into something brutally pragmatic: where rationing is enforced by AI and descent is a luxury no one can afford. The eerie reality, these scenarios aren't just hypothetical, they are inevitable in any long-term settlement. The only question is whether we'd adapt fast enough to outthink the storm or become another whisper lost in the clouds. The unsettling truth is that gas giant colonization isn't about avoiding disaster. It's about designing civilizations that can fail gracefully, where every catastrophe teaches the survivors to build back smarter. Because in the end, the storm doesn't care about courage or ingenuity. It just is, and we'd either learn to live with that or join the countless others who underestimated the sky. Living in perpetual suspension among the swirling storms of a gas giant wouldn't just change how humans survive, it would rewrite the very fabric of culture. Imagine art that doesn't hang on walls but floats in three-dimensional galleries, where sculptures ripple like wind-blown fabric and holograms pulse in time with atmospheric currents. Without horizons or solid ground, traditional landscapes would vanish from paintings, replaced by abstract swirls of color mimicking cloud bands or immersive projections that simulate the lost sensation of standing on Earth's surface. Music might evolve to incorporate the deep, resonant hum of habitat machinery or the eerie whistles of wind against structural cables, blending synthetic tones with the planet's natural acoustics. Every creative expression would become a negotiation with the environment, a dance between human imagination and the ever-present fury just beyond the walls. Religion and spirituality would face their own metamorphosis. On Earth, faith traditions often revolve around sacred mountains, rivers, or celestial bodies, anchors to the tangible. But in a gas giant, where the divine might feel more like the capricious storms themselves, rituals could emerge to honor or appease atmospheric forces. The Great Red Spot might be personified as a deity, its centuries-long rage interpreted as both destroyer and life-giver, shaping seasonal festivals tied to storm cycles. Prayer could involve tending to the fragile systems that keep the city afloat, turning maintenance into sacrament. And without day or night as we know them, time itself might be marked by celestial mechanics, like the eclipses of moons passing through Saturn's rings, creating calendars divorced from terrestrial rhythms. Identity would fracture and reform under these skies. Generations born in the clouds would lack any instinctive concept of up or down. Their bodies adapted to high gravity and their dreams filled with falling not toward ground but into endless voids. The very word home would shed its earthly connotations. Instead of rootedness, it might evoke motion, a sense of riding the eternal winds. Language would sprout new metaphors, phrases like weathering the calm or drifting together, replacing terrestrial idioms about solid foundations. And with Earth visible only as a faint blue dot in the distance, nostalgia could morph into something stranger, a mythic longing for a planet most have never seen, its forests and oceans reduced to legend. The most profound shift, though, might be in how these sky dwellers view themselves. Cut off from terrestrial ecosystems, they could develop a dual identity, part conquerors, part hostages, proud of taming the untamable but forever conscious of their fragility. Civic pride might center on engineering marvels, like the oldest habitat still riding Jupiter's jet streams after centuries, while cautionary tales warn of cities swallowed by storms. Over time, this could forge cultures that value adaptability above all, where children are taught to fix air filters before they can read, and where storytelling preserves the lessons of those who first dared to call the clouds home. Yet the greatest artistic masterpiece of a gas giant civilization might be invisible, the collective resilience of people who have learned to thrive where nature insists they shouldn't. Their culture wouldn't just reflect their environment, it would be a mirror held up to humanity's endless capacity to reinvent itself, even when the sky refuses to cooperate. Life on Earth has a stubborn habit of thriving where it shouldn't. Places so hostile they make gas giants seem almost welcoming by comparison. Take the scalding hydrothermal vents at the bottom of the ocean, where temperatures soar past 400 degrees and toxic chemicals spew from the planet's crust. Here, entire ecosystems flourish in perpetual darkness, sustained not by sunlight but by chemosynthesis bacteria converting sulfur and methane into energy. Giant tube worms armored in heat-resistant proteins host these microbes in their flesh, forming a symbiotic partnership that defies everything we thought we knew about life's limits. Or consider Chile's Atacama Desert, where bacteria survive in soil so dry and irradiated it's nearly indistinguishable from Mars. These extremophiles don't just endure, they've evolved tricks that border on science fiction, from DNA repair enzymes that fix radiation damage to proteins that fold correctly even when boiled. Now apply those lessons to a gas giant. The organisms clinging to Earth's most brutal niches prove life doesn't need gentle conditions. It needs chemistry, energy, and time. Jupiter's violent atmosphere might seem sterile, but its layers contain gradients of temperature and pressure not unlike Earth's ocean depths. Microbes here could exploit the turbulence itself, riding updrafts to cooler zones when temperatures spike or sinking to harvest chemical energy from deeper, hotter layers. Some extremophiles on Earth thrive on hydrogen gas, a trait that would make them right at home in Jupiter's hydrogen-rich skies. Others, like the acid-loving archaea in Yellowstone's hot springs, demonstrate how life can flourish in pH levels that dissolve metal. If similar organisms drifted in the sulfuric clouds of Venus, why not in the ammonia-laced bands of Saturn? The real gold mine lies in biomimicry, stealing nature's blueprints. Deep-sea creatures like the snailfish survive pressures that would flatten submarines, thanks to flexible membranes and proteins that resist compression. Engineers might copy these designs for gas giant habitats, creating structures that flex with atmospheric currents rather than resist them. Then there's tardigrades, the microscopic water bears that survive vacuum, radiation, and temperatures near absolute zero by entering suspended animation. Their secret, a sugar called trehalose that glassifies their cells, preserving them until conditions improve. A civilization floating in Neptune's radiation belts could harness similar biochemistry, crafting synthetic trehalose to protect crops or even human tissues during solar flares. But the most radical insight isn't about survival, it's about transformation. On Earth, life reshapes its environment to suit its needs, from cyanobacteria oxygenating the atmosphere to coral reefs building islands. In a gas giant, organisms might evolve to exploit the atmosphere's chemistry, perhaps metabolizing acetylene or converting atmospheric methane into complex organics. Imagine a future where cities don't fight the storm but recruit it, seeding the clouds with engineered microbes that stabilize turbulence or filter toxins. The line between biology and technology would blur, turning the planet itself into a partner rather than a foe. The lesson isn't just that life is resilient. It's that life is inventive, turning every obstacle into an opportunity. If microbes can thrive in nuclear reactors or Antarctic ice, then the clouds of Jupiter aren't a death sentence, they're a challenge waiting to be met. And the solutions might not come from our labs, but from creatures that have already solved the universe's hardest puzzles, one extreme at a time. Predicting when humanity might plant its flag in the swirling depths of a gas giant isn't just guesswork, it's a collision of optimism, physics, and sobering reality. Most experts peg the timeline somewhere between laughably distant and maybe never, but drill deeper, and you'll find fascinating splits in the futurist camp. Take Dr. Isaac Arthur, a prominent astrophysicist and futurist, who suggests that with aggressive technological advancement, floating habitats in Jupiter's upper clouds could materialize within 2 to 3 centuries. His argument hinges on exponential progress in fusion power, nanomaterials, and AI technologies already in their infancy today. But then there's the counterpoint from Dr. Kevin Heng, an exoplanet atmospheres specialist who calls even 500 years wildly optimistic. citing the sheer scale of unproven engineering required to tame storms larger than Earth itself. The debate centers on what we're willing to assume. If humanity maintains its current pace of innovation, no apocalyptic setbacks, no prolonged stagnation, then the 23rd century might see robotic outposts testing atmospheric mining in Saturn's less hostile layers. These wouldn't be cities yet, more like the Antarctic research stations of space, cramped, perilous, and utterly dependent on supply lines from the inner solar system. But full-blown colonization, that's where the numbers explode. Building self-sustaining metropolises demands technologies that sound like magic today. Force fields to deflect radiation, materials that self-repair under crushing pressures, and fusion reactors small enough to float yet powerful enough to outlast eternal storms. Even the most bullish timelines, like those from the Lifeboat Foundation's space habitability studies, concede that these breakthroughs likely won't converge before the year 2500. Then there's the wild card, artificial intelligence. If we manage to develop super-intelligent AI within the next century, a big if, the entire timeline could compress. Machines don't need breathable air or radiation shielding, and they could design solutions to gas-giant challenges at speeds human brains can't match. Futurist Anders Sandberg speculates that AI architects might crack the problem of floating cities in decades, not centuries, by running trillion-fold simulations of atmospheric dynamics until they find stable configurations invisible to us. But this path carries its own existential risks, like handing the keys to our future to entities we might not fully control. The darkest timeline, one where we never make it at all. Historian Stephen Webb, author of If the Universe is Teeming with Aliens, Where is Everybody?, points out that civilizations often hit ceilings, whether from resource depletion, war, or simply losing the drive to explore. If humanity turns inward, prioritizing virtual worlds over physical expansion, gas giants might remain forever out of reach, their storms raging untamed long after we've forgotten how to dream beyond our own atmosphere. Yet amid these extremes, one truth stands out. The time frame isn't just about technology, it's about will. The pyramids weren't built because the physics of stone stacking was easy. They rose because a society decided the effort was worth it. Gas giant cities will happen when, or if we decide they must. Maybe that moment comes after Earth's first climate collapse scares us into becoming a multi-planet species. Maybe it waits until a child born today stares up at Jupiter through a telescope and refuses to accept that anything is impossible. The real deadline isn't in the stars, it's in us. Before we bet humanity's future on gas giants, it's worth asking, are there safer, saner options closer to home? Mars has been the darling of colonization dreams for decades, a rusty but familiar cousin of Earth with solid ground, thin but usable atmosphere, and sunlight strong enough for solar panels. The red planet's day-night cycle is nearly identical to ours, and its gravity, though weaker, might be gentler on human biology than a gas giant's crushing pull. Proponents like Elon Musk envision domed cities evolving into terraformed landscapes, where carbon dioxide gets scrubbed into breathable air and underground lava tubes become prefabricated metropolises. But Mars has its own nightmares, radiation levels that would require living underground, dust storms that blot out the sun for months, and soil laced with toxic perchlorates. Compared to gas giants, it's a walk in the park, but that park is still a harsh, airless desert where a ripped spacesuit means death in seconds. Then there's Europa, Jupiter's ice-covered moon. Beneath its cracked, frozen shell lies a global ocean twice the volume of Earth's, warmed by tidal forces and possibly rich in hydrothermal vents. Astrobiologists salivate over the chance to find life there, and engineers dream of subglacial habitats where warmth melts ice for water and radiation is blocked by kilometers of protective frost. But Europa's surface is a lethal no-man's land, bombarded by Jupiter's radiation and cold enough to freeze nitrogen solid. colonies would need to be underwater fortresses, permanently cut off from sunlight and dependent on nuclear reactors or geothermal taps. For all its liquid water appeal, Europa makes gas giants look almost hospitable. At least their skies offer solar energy and escape routes. O'Neill cylinders present a radically different vision, artificial worlds built from scratch in the emptiness of space. Picture gargantuan, rotating habitats tubes miles long, their interiors landscaped with rivers, forests, and towns under domed skies. Sunlight floods in through vast mirrors, while spin gravity mimics Earth's pull without planetary baggage. No storms, no toxic atmospheres, just customizable climates and perfect real estate. The catch, building these megastructures demands space-based industry. We don't yet possess asteroid mining on an epic scale, zero-G manufacturing, and energy sources beyond current fusion dreams. Unlike gas giants where resources float ready-made in the atmosphere, O'Neill cylinders require us to haul every ton of material out of gravity wells. Each alternative forces a trade-off. Mars offers familiarity but demands radical planetary engineering. Europa has water but dooms settlers to eternal darkness. O'Neill cylinders promise utopian control but rely on technologies that might remain fiction for centuries. Gas giants, for all their fury, dangle unique advantages. Limitless hydrogen for fuel, atmospheric mining without digging, and the thrill of exploring frontiers where nature still writes the rules. The choice isn't just about practicality, it's about identity. Will we be planetary settlers content with near-Earth horizons, or will we become something bolder, creatures of the storm, learning to thrive where the universe itself seems to scream impossible? Science fiction has painted gas giants as glittering playgrounds for humanity, floating cities bathed in golden light, where citizens stroll across open-air platforms suspended above endless storms. Take the cloud cities of Jupiter, a classic tale where characters sip cocktails on verandas overlooking the Great Red Spot as if it were a scenic canyon. These visions are seductive, but they clash brutally with reality. The truth, Jupiter's upper clouds are a -150°C freezer. Its landscapes are supersonic hurricanes, and its sky is a corrosive soup of ammonia and hydrogen sulfide. Fiction glosses over the fact that any structure exposed to those winds would be sandblasted into debris within hours, or that radiation levels would fry unshielded humans like ants under a magnifying glass. Where stories really jump the rails is physics. Films and books often treat gas giants as giant, slightly moody versions of Earth, ignoring the fundamental weirdness of an environment where down is a meaningless concept. In 2010, Odyssey 2, Arthur C. Clarke's explorers float gently through Jupiter's atmosphere in a balloon-like craft, casually observing exotic life forms. The reality, balloons there wouldn't drift, they'd be shredded by wind shear or crushed as they sank into layers where hydrogen behaves like liquid metal. Even Star Wars' Bespin, with its elegant platforms and breathable air, handwaves away the fact that a gas giant's atmosphere lacks the oxygen mix humans need. The moment you opened a window, everyone would suffocate faster than you could say, "Han shot first." But fiction isn't useless, it's a compass pointing toward possible futures. The Integral Trees by Larry Niven imagines life thriving in a gas torus, a ring-shaped habitat orbiting a planet. While not a gas giant itself, the idea of organisms adapted to free-floating existence hints at real astrobiological possibilities. Similarly, Alastair Reynolds' Terminal World features floating cities on a gas giant, but grounds them in speculative tech like anti-gravity, acknowledging the sheer improbability of building there with known science. These stories succeed by embracing the constraints, then bending them with plausible leaps. The biggest divergence between sci-fi and reality: scale. Movies show cities dwarfing the Great Red Spot, but Jupiter's storms are planetary behemoths Earth could drop into one with room to spare. a small weather system on Saturn could swallow continents. Fiction shrinks these giants to fit human drama, but the real awe lies in their incomprehensible vastness. No Bespin skyline could dominate that canvas. Our grandest structures would be dust motes in the storm. Yet for all their inaccuracies, these stories serve a purpose. They inspire scientists to ask, could we? When Carl Sagan speculated about floating life in Jupiter's clouds, he wasn't spinning fantasy. He was challenging biologists to rethink life's boundaries. Every tale of cloud cities, no matter how fanciful, nudges us closer to the day when reality might catch up to the dream. The truth may lack Hollywood's shine, but it's far stranger. A future where we don't conquer gas giants, but learn to humbly exist within them on terms the universe itself dictates. Would you trade blue skies and solid ground for a life suspended in perpetual storm? The idea of colonizing gas giants isn't just a technical challenge, it's a psychological experiment waiting to happen. Surveys on extreme space habitation reveal a fascinating divide in public willingness, with responses often splitting along lines of risk tolerance, generational outlook, and even cultural background. A 2023 study by the Interplanetary Society found that while 78% of respondents supported Mars colonization in theory, only 29% would personally volunteer for a one-way trip. When the question shifted to gas giants, that number plummeted to 6%, roughly the same odds people gave for skydiving without a parachute. Dig deeper, and the reasons become visceral. Humans are hardwired for horizons, for the reassurance of ground beneath our feet. Psychologists attribute this to topophilia, our innate emotional bond to landscapes. Gas giants violate every instinct: no sunrises, no open spaces, just an endless ocean of clouds stretching into oblivion. Participants in UCLA's simulated gas giant habitat study reported disorientation and anxiety within days, with some describing the experience as living inside a haunted snow globe. Yet outliers exist. The same studies identified a slim but passionate minority, often extreme athletes, deep-sea researchers, or veterans of isolated outposts who described the prospect as thrilling rather than terrifying. For them, the gas giant's fury wasn't a deal-breaker, it was the ultimate adrenaline rush. Cultural narratives play a surprising role. Countries with strong maritime histories, like the Netherlands or Japan, showed marginally higher acceptance rates in polls, possibly due to ancestral familiarity with battling uncontrollable natural forces. Meanwhile, nations with spacefaring traditions, Russia's cosmonaut legacy, America's Apollo-era nostalgia, produced more volunteers, but only if framed as pioneering rather than exile. Marketing matters. When the European Space Agency rebranded a hypothetical Jupiter mission as cloud surfing instead of storm dwelling, interest surged 40% among 18 to 35-year-olds. The generational gap is stark. Millennials and Gen Z, raised on climate crises and VR escapism, were twice as likely as baby boomers to consider gas giant habitation, though their motives differed. Older respondents cited practicality, resources, overpopulation, while younger ones leaned into existential appeals. Earth feels like a sinking ship anyway, or why not try something radically new? This mirrors a broader trend in space advocacy, where younger demographics view interplanetary migration as an inevitable evolution rather than a last resort. Corporate interest adds another layer. Private space firms like Axiom and Blue Origin have quietly funded focus groups probing public appetite for non-terrestrial lifestyles, with revealing results. Participants shown concept art of floating biodomes amid pastel cloudscapes were 50% more likely to express interest than those shown technical schematics of pressure valves and radiation shields. Aesthetic storytelling, it seems, can soften even the harshest realities, but the enthusiasm faded when confronted with hard numbers. A hypothetical 20% mortality rate per decade from equipment failure or radiation exposure slashed volunteer interest to near zero. The most telling data comes from analogs. Antarctica's McMurdo Station, often cited as Earth's closest parallel to off-world colonies, sees annual turnover rates of 80% despite six-figure salaries and modern amenities. Workers cite isolation, confinement, and the unnerving sameness of the landscape as deal-breakers issues gas giants would magnify exponentially. Yet the same studies uncovered a counterintuitive twist. After 3 years, a subset of Antarctic lifers reported feeling more at home on the ice than in their native cities. Psychologists call this the inversion effect, where extreme environments rewrite human comfort zones. Gas giant settlers might not just adapt, they could come to crave the storm. What emerges isn't a yes or no answer, but a spectrum of human audacity. For every 1,000 who'd never leave Earth, there's one who'd sign up tomorrow, lured by the challenge or the chance to etch their name in cosmic history. The real question isn't whether people would go, it's whether we'd need generations born in orbit to truly call those clouds home. After all, humanity didn't conquer the oceans by staying onshore. We built ships, then crews, then cultures that forgot the land existed. The gas giants whisper the same possibility, that the unimaginable only stays that way until someone dares to imagine it first. So, after diving into the crushing pressures, supersonic winds, and radiation maelstroms of gas giants, after dissecting floating cities, exotic materials, and the sheer audacity it would take to call a storm home, where does that leave us? The short answer may be, but that maybe is buried under a mountain of ifs, and when so immense it defies imagination. Let's be clear, nothing about gas giant colonization is impossible by the laws of physics. The universe doesn't forbid it, it just laughs at the idea, tossing up barriers that make Mount Everest look like a speed bump. We've landed probes on comets, built labs under Antarctic ice, and sustained astronauts in orbit for years. The raw ingredients for survival are there: hydrogen for fuel, thermal gradients for energy, and vast atmospheres to mine for resources. But here's the catch: every solution requires technology that either doesn't exist yet or exists only as scribbles on a theoretical physicist's whiteboard. Take fusion power. Without it, floating cities are non-starters. Solar energy can't penetrate those thick clouds, and chemical fuels would be laughably inadequate. Even if we crack fusion tomorrow, scaling it to withstand hurricane-force winds while floating in a corrosive soup of gases is another challenge entirely. Then there's material science. We'd need substances that laugh off pressures capable of turning diamond into putty, that self-heal when cracked by ammonia-laced winds, and that somehow stay lightweight enough to avoid sinking into the abyss. Graphene and aerogels are promising, but they're still in their infancy, like showing up to a sword fight with a butter knife. And what about time? Even if every breakthrough happened on scheduled fusion by 2050, metamaterials by 2070, AI smart enough to manage atmospheric chaos by 2080, we're still talking centuries before the first viable habitat could deploy. That's assuming no wars, no economic collapses, no global crises that divert humanity's attention and resources back to earthbound survival. The timeline isn't just long, it's littered with scenarios where the dream gets shelved indefinitely. But here's the twist: impossibility has a way of shrinking when humanity decides to stare it down. The Wright brothers were told powered flight defied physics until it didn't. The moon landing was a fantasy until boots crunched into lunar dust. Gas giants might be the ultimate test of that stubborn human trait, the refusal to accept limits. The real question isn't whether we can conquer these worlds, but whether we'll muster the collective will to try, because the universe doesn't hand out victories. It waits to see who's bold enough to take them. So, possible, technically, yes; practical, not in our lifetimes or our grandchildren's. But if history's taught us anything, it's that today's science fiction has a habit of becoming tomorrow's breakfast conversation. The storms will keep raging, the clouds will keep churning, and somewhere in that chaos the seeds of an answer are waiting. Whether we'll be there to plant them is a story only time can tell. From floating cities riding eternal storms to ethical dilemmas over potentially disrupting alien ecosystems, the dream of gas giant colonization forces us to confront both the staggering potential and sobering limitations of human ambition. We've explored how habitats might harness fusion power from endless hydrogen reserves, how nanomaterials could flex like organic tissue under crushing pressures, and how societies might evolve in skies without horizons. Yet for every engineering breakthrough, self-repairing structures, radiation-defying shields, there's a counterweight of existential risks, from lethal radiation belts to the psychological toll of life adrift in perpetual twilight. The ethical dimension looms just as large as the technical hurdles. Would mining Jupiter's helium-3 justify disrupting atmospheric layers that might harbor life? Could we avoid repeating Earth's colonial mistakes on a cosmic scale? These aren't abstract debates, they're rehearsals for humanity's next great inflection point, where survival instincts collide with interstellar stewardship. What makes gas giants so mesmerizing isn't just their scale or their fury, it's how they expose the edges of our imagination. They challenge us to innovate beyond planetary thinking, to design civilizations that don't conquer environments but harmonize with them. Whether we'll ever call those swirling depths home remains uncertain, but the pursuit itself reshapes what's possible. Now it's your turn. Could we tame these titanic storms, or are some frontiers better left unexplored? Drop your thoughts below. Are gas giants humanity's next chapter, or a cosmic daydream too far? Let's keep the conversation soaring.